Hello everyone, welcome back to my tutorial. In this tutorial we are going to solve a bar deflection due to self-height. So the material we are taken is a steel material. So this is our model. So 1 meter length and 0.1 and 0.1 meter is a cross section. In previous case we have applied gravity in this perpendicular direction. Now we are going to apply gravity in axial direction. So let's get started. So just open the Salome meca. Salome meca is the wonderful pre-post processing and finite element software. So it has the code aster, is good capable of solving thermomechanical and analysis. So now I'm just moving into geometry model. So I'm just using this one, 1 meter length. This one is 0.1 and 0.1. Just fit screen. This is our model. Apply and close. Now we have created the model. Then just create the group for applying the boundary conditions. Now I just want to fix it here. Fix, apply, close. This one boundary condition is enough for this case because we are going to apply load as a gravity. So to the whole body. So now we'll save this file, go to save as, bar. I'm just saving here. Now we are done the meshing geometry modeling. Now just move into mesh model. Choose the box, mesh, create mesh. I'm just choosing hexagonal element. 2D is quadrangle mapping. 1D we just make it white discretization, local length of 0.02. Apply and close. Compute. Now we are done meshing. See here we have taken the group also. Now we can save this file. Now we'll move into aster study. Just click this aster study. Stable, save OK. Now just create stage, add stage. Now we'll add one by one. First read the mesh. Read a mesh. Mesh 1 is our mesh. Just apply. Format you can give it as MED. Just apply, save OK. Now just go to definition of model, assign finite element model. Finite element. Apply to all, yes. Mechanic, choose mechanic. 3D, OK. Just apply it, save OK. Now we have done model definition. Now go for material. First define a material. So ours is linear elastic isotropic material. So edit. We need to define density for self-height problems. So 210 e power 9. This one is 0.3. This one is 7860. OK. Here you can rename also. I'm just giving steel. Apply, save OK. Now we have defined the material. Now we just want to assign the material to the model. Go here, assign material. Just whatever the name is coming is keep it the same. Mesh, model. Here material assignment. Just click it here. Everywhere. Save OK. Then apply it. Save OK. Now we have assigned the material also. There is no function on the list in this case. Just leave this option. Go to boundary condition and loads. So there is an option called assign a mechanical load. Just to choose that one. So here we need to define gravitational, edit. So our gravitational constant is 9.81. Click this three items. We now in previous case we have applied gravity in z direction. So now it will bend like this. It like a beam. Now in this case we need to apply a gravity in x direction, then only it is gravitational, it's become bar. So now I'm just, x direction means the first 0 1, here I'm specifying it into positive 1, this direction it's pulling down, remaining we make it 0. So 9.81 is the constant, is acting in positive x direction. Say OK. Then we need to fix left side. Go to a face info, here group element, choose it this fixed group, say OK. Just fix this 3 directional, 0, make it 0 0, say OK, apply it, say OK. Now we have created constraint as well as the gravity load. In pre-analysis just go, so there is no pre-analysis we need to do, just leave this case, go to analysis, our case is static mechanical analysis, keep this clean, choose material is field mat, model is model, here there is an option called load, choose the load as a load, say OK. Remaining things you keep it same, just apply it, say OK. Now we have defined the solver. Now we just want to calculate the, what the solver will do, it will calculate the displacement, the primary value only it will calculate. From that we need to derive stress, strain, everything. Further just go to force processing, call champ, give the same name, Roslin. Constraint means directional stresses we can choose. Sigma LNO means element in directional stresses, sigma. Node, sigma in node. Similarly criteria, choose equivalent LNO, equivalent node. Now we have done, scroll down here, choose model and material. From the mechanical static it will derive, just apply it, say OK. Now you see here calc camp also done, just leave this fracture and fatigue, just go to output, we need to save the output, so click this triple button, pictures, code aster, gravity, bar, I'm just giving name as result.rmed, save. Now I have given the name. Now we need to take that values, go to edit, mesh, result. Here we need to choose calc champ, go for calc champ, remaining thing you leave it. Here there is an option called tau champ, make it S, remaining thing you leave it, say OK. Here the format to make it MED, apply it, say OK. Now everything is done. Now just save this file, go to history view, here just click this plus button and click this one also, make this into 5 seconds, run it, just wait for a while, it will solve. If any error comes it will show here, based on that we need to rectify it. Now see it, the solver is solved. So everything is done correctly. Now we can do the post processing in Paravis. Go to Paravis, just right click this one, pictures, code aster. So our file is result.rmd, select this one, here you can see, just apply it. Now go to displacement. To change the color view, just make this into rainbow, blue to red, apply it, close. Now again go for TX. This is the actual deformation. you want to see in deformed shape, just go here, make it 12, then make it 10 also, make it 15, 12 is enough. If you want to see the deformed shape, just click this one, wrap vector, 50% of scale I'm giving, apply it. So now we see it's deforming in axial direction. Similarly, we can see the stress, go for sigma x, make this into rainbow, blue to red, apply, close. Now you just make this into 12. So this is the axial stress due to self weight. This is acting like a bar. So in that we have completed the deflection due to self weight. Thank you for watching my video. Please subscribe my channel in more videos. Thank you.